Now we're going to take a look at a couple of equations where the log will appear. So we're going to start with something that contains a log rather than something that contains an exponential. So to solve an equation containing logarithms, what we are going to do, at least my approach, is we're going to exponentiate both sides of the equation. The property that we're going to use says the following. If a equals b, then 10 raised to the a equals 10 raised to the b. Let's take a look at a rather simple equation, but it'll have a few steps. So let's solve for x. If we have 6 multiplied by the log of x plus 1 equals 4. Like we did in the previous exponential equations, what I'm going to first do is isolate the logarithmic piece. Doing so gives me the log of x plus 1 equals 4/6. I divided both sides by 6. Now I'm going to exponentiate both sides. So I'm going to take 10 and raise it to the left-hand side, 10 raised to the right-hand side. Doing this gives me 10 raised to the log of x plus 1 equals 10 raised to the 4/6, which would be the same as 10 raised to the 2/3. Now again, if I remember my properties of exponential and logarithmic functions, when I have 10 raised to the log of something, the 10 and the log, being inverses, cancel each other out and just give me x plus 1. So I end up with x plus 1 equals 10 to the 2/3. And now I have one last very simple step to solve for x. I end up getting x equals 10 raised to the 2/3 minus 1, which I could put in the calculator and estimate out, but I think for right now I'm just going to leave it in that particular form. Let's take a look at one last example, and this one's quite involved. I'm going to solve for x, and I have the log of x plus the log of x plus 3 equals 1. Now the first thing you might notice is that the logs are both on the left-hand side, and that's a good thing. Now the thing I don't like so much, though, is that I have two logs, and I'd like to rewrite this as an expression that contains a single logarithm. So if I remember my properties of logarithms, I would remember that the log of x plus the log of x plus 3 would be the same as the log of x times x plus 3. And so I can use my property of logs that said log of ab is log of a plus log of b, except I'm using it in reverse. So then I have the log of x times x plus 3 is equal to 1. Now, like I did in the previous example, I can exponentiate both sides. So I get 10 raised to the log of x times x plus 3 equals 10 raised to the first. Now I happen to know what 10 raised to the first is. That's just 10. So I get x multiplied by x plus 3, because the 10 and the log canceled out, equals 10. And now I need to solve this quadratic equation. Remember, the way I solve a quadratic equation is I need to multiply this out, bring the 10 over so it's equal to 0, so I can factor or use my old friend, the quadratic formula. So doing so, though, simplifying this gives me x squared plus 3x minus 10 equals 0. And this one's rigged a little bit so that it factors. So that would actually factor into x plus 5 multiplied by x minus 2 equals 0. And when I solve, I get x equals negative 5 or x equals 2. The thing that we need to be a little bit careful of, though, is we need to be careful with these problems that our answer actually checks. And if I went back and I tried substituting negative 5 into my original equation, what I would learn is back in the original equation, x equals negative 5 is not a legitimate domain value. It does not check in the original equation. The 2, the x equals 2 will, and so the only answer to the problem is x equals 2. So even though it looks like I get two solutions, only one of them checks, only one of them is an actual answer to the original question. These are a little bit tricky to do, and so you'll want to make sure you go back and do these, as well as several of the exponential questions, to make sure you're very comfortable with all of the different things that can happen. It's very important that you practice these over and over and over again.